Picture this. You're standing on solid ground, maybe sipping coffee, when I tell you something the size of whole continents is still falling beneath your feet, and it's been falling since before the dinosaurs vanished. Sounds wild, right? Well, that slow-motion plunge is the hidden story we're unpacking today. Here's the plan for the next 10 minutes. First, we'll visit the underworld, where ancient tectonic plates keep on sinking. Then, we'll eavesdrop on the planet to find out how scientists map those movements. Finally, we'll explore why these deep Earth traffic patterns can nudge earthquakes, volcanoes, and even future coastlines. Ready? Let's dive. Think back to your school textbook picture of Earth's interior. Neat colored bands, heat drifting up like a calm conveyor belt. Turns out that picture is way too tidy. A brand new global survey shows the deep mantle is more like a twisted, shifting loom of rock. Plates that dove into the planet 100, 200, even 300 million years ago are still warping everything around them. They form giant underground fault lines that steer heat, push continents, and load stress into the rigid shell we live on. Let that sink in for a second. The deep Earth remembers where the surface once tore itself apart, and it's still acting on that memory today. So, how on earth, literally, do you study something buried 2,000 kilometers down? You turn the planet into a giant listening lab. Every earthquake becomes a probe. Each one shoots vibrations through Earth, and thousands of seismometers quietly capture the echoes. Over 3 decades, scientists built a massive library of these wave patterns. Then they handed the data to supercomputers, which unraveled the distortions into 3D strain maps. Here's the breakthrough. Earlier models only showed hot spots and cold spots. The new maps show where rock is actively twisting, stretching, and folding right now. Think of it as a live strain weather map for the lower mantle. First key point. Those high-strain corridors line up with the ghost paths of plates like Farallon and Tethys, the slabs that plunged long ago. The deep mantle, in other words, still carries their fingerprints. Second key point. Deformation changes everything. In the most tortured zones, minerals realign, like playing cards shuffled into a new deck. That tweak in their crystal fabric changes how fast seismic waves travel, which is how researchers spotted the zones in the first place. But it also changes how easily water, carbon, and radioactive elements move, turning some areas into express lanes and others into roadblocks for Earth's deep chemistry. Third key point. Sinking slabs drag surrounding mantle with them, concentrating flow into narrow downwellings. Between those sinking tracks, gentler upwellings rise, lifting broad swaths of mantle. Over tens of millions of years, that push-pull can nudge whole regions at the surface higher or lower, quietly altering sea level, erosion patterns, even the stability of future ice sheets. Take a breath, because we're still going deeper. The maps also hint that the lower mantle isn't one uniform layer after all. Some depths fight deformation, others give way easily. That tells us minerals may be changing phase or grain size as pressure mounts. Those subtle shifts control how fast slabs sink, how long they park, and where their material finally resurfaces, maybe in a hotspot thousands of kilometers away. And because we can now tie each strain corridor to a specific ancient plate, we've got a new test for plate tectonic reconstructions. If a computer model says an old slab should sit under the Atlantic, the strain map can confirm or call foul. Imagine the lower mantle as an ancient rail system. The tracks were laid hundreds of millions of years ago by sinking plates. Today's trains are slow currents of solid rock creeping a few centimeters a year. Where tracks intersect, traffic jams form. Rock piles up, heats differently, and sometimes feeds long-lived volcanic hotspots. In other places, the tracks funnel trace elements and water like freight cars moving down a single line. Give that process 50 million years, and it can shift where continents grow new crust, where ocean floor is recycled, and where deep carbon hides until its next ticket to the surface. So what? Well, these strain maps let scientists forecast geological change almost like long-range climate models. By knowing the slow traffic patterns in the mantle, we can anticipate which coastlines might rise or sag, where new mountains might root, and even where critical minerals could concentrate. Pretty handy for the next generation of planners, and for anyone curious about Earth's future. Alright, let's pull the threads together. Ancient tectonic plates that sank ages ago are still falling, warping Earth's deep interior as they go. A global listening network turned earthquake echoes into a live 3D strain weather map of the mantle. Those maps show high-strain corridors that match the ghost paths of old plates, revealing hidden rail lines that steer heat, elements, and even the rise and fall of continents. The lower mantle isn't uniform. It's a layered maze that decides how fast slabs sink and where their materials eventually pop back up, sometimes as volcanoes halfway across the planet. By decoding these deep Earth traffic patterns, we gain a brand new tool for forecasting long-term changes to coastlines, resources, and climate feedbacks. So next time you glance at a globe, remember you're looking at just one frame in Earth's slow-motion movie. Beneath every continent and ocean, ancient plates are still on the move, quietly scripting the planet's next chapters. And now, you know how to read the subtitles.